Well, let's use this as an opportunity to jump into our material for today. We are getting started with, we'll be talking about the first week of course 5. This week is starting to talk about deploying models, and we will discuss Spark and Docker and Flask. I think that continues into the second week of this course. I guess this is a good opportunity to congratulate all of you. We're almost at the finish line here. The next couple of modules in course 6, get into build on deployment and talk about kind of once you've got a model into production, how do you monitor it? And we'll talk a little bit about technologies like OpenScale and Kubernetes. And I'll talk about Kubernetes today probably because I've used it in part of the examples here, just on my personal deployment. But before we jump in, kind of the usual check-in. Where is everybody in terms of the course? Tracy, it sounds like you're caught up. Modulo struggling with Docker a little bit.
Yeah, I haven't even started on the project for week 1 because I, wasted all that time trying to get Docker and CUDA configured and am still stuck in a non-successfully configured space. So I still have to work on that.
And Jose, you're a week or 2 behind now, or further, or?
Just 2 weeks behind, just the last 2 weeks. But I'm following along as best I can. I haven't done the projects. I'll try to get them here in the next couple of weeks, but yeah, 2 weeks behind.
Okay. How about you, Jess?
I'm 2 weeks behind as well.
Okay. Cool. Well, we'll talk through some of the deployment stuff today, and just kind of reflecting on course 4 and course 5. Course 4 talked a lot about the model evaluation and the performance metrics and model training and building pipelines and things like that. Course 5, on the other hand, is much more kind of infrastructure focused. So all of the models that we're building, at least in the first week, are fairly simple, but it's a very different set of skills and material that's covered. But we'll just dive into it. So the learning objectives for course 5 are to become familiar with Spark and various Spark concepts like RDDs, data frames, and pipelines in Spark, to use Spark Submit to interface with Spark environments, to get familiar with Flask and Docker, and to use a Flask app alongside Docker to deploy a machine learning model, and then to deploy an ML model from Watson Studio to Watson Machine Learning. The past couple of courses and this one included various Watson things that we haven't gone over in our sessions, mostly because they've, like in this one, the Watson example was kind of at the end, and I bumped up against time, but I'm going to catch up on all that kind of stuff, and in the next session or 2, we'll go through all of the various Watson examples so you're familiar with the tools and how they work. So This module starts off with some kind of high-level commentary around productionalizing models. And it's, really good advice that is similar to the, kind of advice offered, in training models. Basically start simple, get your end-to-end, well, in the case of, training, it's like get your end-to-end pipeline working and then worry about, getting your optimization, getting your model to perform better. It's a very similar concept here. Get a basic model working, get it, get a pipeline in place to get the basic model deployed, then make your model better through optimization. And then, once your model's performing at a level that you need it to perform at from a accuracy or metric perspective, then worry about making your model faster to meet your needs. There's some high-level discussion on how you would go about making your model faster. We don't really talk about this in much detail in this module, but some of the things that you want to keep in mind are, first and foremost, using the appropriate data containers in Python. So for example, you can see pretty significant time differences when you're working with large data sets. If you're using, for example, the example they give here, Python set is going to be a lot faster than a Python list. And similarly, NumPy arrays are going to be a lot faster than Python lists. And so you want to use the faster data types whenever possible. Beyond that, there are, tools that are, both, multiprocessing, threading and subprocessing are Python modules that work at different levels of abstraction that allow you to spawn out processes and distribute work to those processes. Those are all fairly low-level tools. Similarly, you've got libraries like MPI that deals with message passing and is used for high-performance computing fairly significantly. And IPy Parallel, I've not come across that before, but it's another parallel computing tool. In the case of all of these, you're really starting to think about distributed computing, and you're generally not going to go here unless you are working at a pretty large scale, and you're probably in a production environment and have access to an engineer with distributed computing experience that can help out with this kind of stuff. The next couple things are, more common to see. Cython is a C compiler for Python that allows you to produce C extensions for the portions of your code that are slow. And CUDA is a kind of a software layer that sits between the frameworks that you're using, like TensorFlow and others, as well as between that software layer and your NVIDIA GPUs to allow those software layers to take advantage of the GPUs. And often there are a lot of optimizations that are built in via CUDA. And so CUDA is often, particularly when you're working with deep learning, most of the frameworks, if you've got a GPU in place in your system and you've got all of the drivers set up correctly, which is a task that's easier said than done in many cases. But if you've got all that working correctly, then the performance optimizations that come with CUDA often come for free and are baked into the various software frameworks that you were using. Tracy, were the issues that you were running into CUDA driver type issues?
Yeah, yeah. Things were installed, but for instance, I would bring up, I'd try to look for devices and I would have problems initializing CUDA from inside, or and other things just would like, hey, I can't find any GPUs available. So it might have been something, I've had something like that happen before where I just needed to do a hard reset of the computer or hard reboot of the computer. So maybe that will fix some of it, but I threw in the towel late last night.
Yeah, yeah.
One of the things that I was surprised they didn't really drone on, this is almost always, droned on whenever you start talking about optimization, is Knuth's, famous quote, premature optimization is the root of all evil. I was really surprised they didn't harp on that.
Well, they didn't harp on that using that quote, but I think the previous slide was really focused on the same idea, which is making it faster is the kind of the last step in a series of steps, and you really only do that if you need it. The first step is, again, make it work, make it better, make it faster. So they did drone on that, but not the specific Knuth quote.
I guess I'm curious because I don't typically work with things at this level where it's needing to be really fast, for production. Mm-hmm. Excuse me, but is this a very important part of the process, I guess, in industry? Because I guess I'm just thinking of most of the use cases where I've seen, and it's sort of like often portrayed almost a little bit like afterthought. Like if we could make it faster and it was easy to do so, we would maybe do that. But it often, I feel like, is not particularly emphasized. So I'm just wondering, is that just my perception, or is that how it is in practice, or sort of what's the status of this side of it?
Yeah, I think this side of it is very important, particularly, and the course talks about kind of the idea of scale and what that means, and are some different definitions of scale. But if you think about kind of the general workflow, a lot of the time that a data scientist will spend is on kind of exploratory tasks and data munging and trying to find a model that works and building a model. And what we often see in enterprises that are kind of early in the maturity cycle is that, okay, we've got a data scientist that creates a model, and then, there's this wall, between, having a model that works on a laptop and getting it into production. And all of the stuff that we're talking about here comes up in the, in getting those models into production. But it depends a lot on the scale that you're operating at. So I did an interview with Jeff Dean, who is kind of a legendary engineer at Google, now the head of Google AI. And one of the things that he mentioned in that interview was that Google has invested pretty significantly in this hardware project called TPU, which is a tensor processing unit, essentially kind of a specialized deep learning hardware analogous to a GPU, so hardware acceleration. And the entire impetus of that project was them thinking about, if they were, if speech comes a reality, like, speech recognition, like we're seeing on our smartphones now, and they needed to scale out their data centers to support kind of some nominal percentage of search queries coming in via speech recognition, using kind of the hardware of the day, they would have to, I forget the specifics, like triple their data center footprint just to accommodate speech inference. And so they set off down a path of building out, investing, millions and millions of dollars, maybe even hundreds of millions of dollars on building specialized hardware. But another part of that is optimizing the software so that it is kind of so that it runs efficiently. And I imagine that they are, doing a lot of work in C and doing a lot of work in low-level programming of these TPUs for applications that are scaled broadly. So, I think it's like, it's probably like a pyramid where, a lot of, the data science work is, runs fast enough on a laptop, and, that's all you ever need to do with it. And, occasionally you might need to, or less frequently, you're scaling out by, doing distributed training using Horovod or something like that, or doing inference in a distributed way on like a Kubernetes cluster. And then, at the, the very peak of that pyramid, your scale is, so much that your infrastructure is so expensive, or your latency requirements, are so, you are kind of unmet by, what Python is able to deliver, that you take steps like this to further optimize.
Jess, I'm in kind of your world as well, the research. So the vast majority of my tools are written for people, like a dozen people or fewer. And so I almost never worry about optimization. But one of the reasons I'm taking the course is that, it's very likely someday I will be in a different situation where scale matters. And I'd kind of like to know ahead of time how I scale up to, 100,000 users from my dozen or so users that I'm currently mucking about with.
Yeah, and that's what I'm thinking of as well. I'm thinking of really health and health science applications, and it's so often kind of a closed box in a hospital system or a research lab, or but of course, the thought is this all becomes personalized medicine and is sort of, broadly available. And then when it is, then this is going to be fundamentally important. Just, thinking of the use cases at the moment, right? So I guess it is sort of a short versus long-term view.
Yeah, it's absolutely use case dependent, very use case specific, and dependent on the, either the scale of your training or the scale of your inference, the extent to which you'll need to, or the scale demanded by your training, or the scale demanded by your inference workloads will kind of dictate the extent to which you need to get into any of this stuff.
Sam, do you think that this will, be a function that has sort of a separate profession, like either software engineers will be doing this part of it, or data engineers would play a role in this as well, in the earlier part of the pipeline of this, or is this going to become something that all practitioners working with deep learning and AI will need to know how to be doing this type of code optimization? Like, would pull out your crystal ball for a second, I guess. Yeah. How will this be structured in terms of work teams and workflow, do you think?
Right. What I tend to see happening in Silicon Valley, which is, maybe the kind of crystal ball for everyone else, is that, early on, there was this, the prevalent idea was that we were going to find these, find or groom these full stack data scientists that, would know how to, both build models and create production level code and, manage that code, get it into deployment. And I think that, some organizations still, do try to hire for, or build a culture of kind of full stack data science. But even on those teams, the skill sets vary, but what I see more often today is that you've got, these teams that include data scientists who are primarily focused on, working with the domain experts on the business side and, building out the models. And they are supported by software engineers, or, sometimes they're even called machine learning engineers, who are focused on the system level requirements of deployment. So, data scientists might come up with a model, and there are machine learning engineers on the team that will take that model and then do the engineering task. So the data science is focused on the science task of we've got data. Is there enough data is there enough signal in our data to build a statistical model that can do prediction, that can predict what we need to predict? And then the machine learning engineer is focused on engineering. Okay, we need to serve X users. We need our latency to be within X envelope. We need our this is our hardware requirements and limitations. Maybe even this is our power requirement and limitations. And so how do I engineer a system that is able to deliver, that's able to deliver kind of this model at the required scale. That said, I think at these organizations that I'm speaking of, data scientists are asked to be more and more familiar with some of the things that we'll be talking about. So for example, at a lot of these organizations, data scientists now are being taught to use Docker, and might be submitting training jobs to Kubernetes, and might be using Git for version control on models. And so I think they're being asked to become more familiar with tools that are traditionally like software development tools, but they are, usually when we're talking about this kind of optimization, that's something that a machine learning engineer might be, more involved in. Maybe with the possible exception of CUDA. Data scientists have been banging their head against CUDA for a long time.
Thanks for that.
Sure. So the next thing that was mentioned is the broad concept of scale, and there was a reference to Amdahl and Gustafson's laws. Not anything that we need to know in any detail, but the main idea with those laws is that if you've got some program, generally speaking, whether that's your training or inference in this case, or any other program, the theoretical ideal is that you can scale scale it linear with the number of processors. So for example, if your training job takes 2 hours and you want it to take 1 hour, the ideal is that you just throw twice as much compute at it. But these laws both say that it's not quite that easy, and if there are parts of whatever process that you have that aren't parallelizable, that are serial, the scaling process is inefficient. And then this is, I think I referenced this earlier. We talked about kind of some of the different definitions of scale. Scale can mean, can I, train, in a training context, can I get my model trained up on the the data that I have in a reasonable time, or if I have a lot more data, can I train my model in a reasonable time? In the inference context, once I have a model, if I am doing an inference, can I get my prediction in the time that I need, you know, given a lot more load or given a lot more data? You know, those are all kind of examples of, you know, some of the implications of scaling that, you know, are often, folks often need to think about. So any questions before we jump into Spark? Where did my Spark picture go? Hold on a second. So Spark is a cluster computing framework. Picture turned invisible. This is very weird. It says it's here. Let's do this. So this is a picture of Spark, and we'll kind of come back to this. But basically, Spark is a clustered computing framework. It is historically, it came out of this idea of kind of big data tools. So big data really was originated with the idea of from a tool perspective with this idea of Hadoop. Hadoop is a software that grew out of tooling that was inspired by at least stuff that Google was doing internally to build the search engine. And so they published this paper on MapReduce many years ago now, and that some folks at Yahoo, I believe, implemented this Google MapReduce paper into a tool called Hadoop. There's actually a guy named Doug Cutting who went on to become the CTO at Cloudera, was the kind of one of the founders of this Hadoop project. And basically what Hadoop allowed you to do was process lots of data on a lot of commodity computers, as opposed to the kind of predominant way to scale up data processing before Hadoop was you need to process a lot of data, you get a bigger computer with, more disk, more CPUs in it, etc. And the bigger those computers got, their costs tended to increase exponentially. And so what Hadoop allowed, folks like Yahoo and others to do was to, instead of buying these $1 million scaled up computers, do the same work by distributing the work across, hundreds or thousands of inexpensive kind of off-the-shelf computers. Each individual computer was kind of disposable, and it used this software layer called Hadoop to kind of coordinate across everything. The Hadoop had a number of different parts, but initially there were kind of two core components. There was this underlying distributed file system, or there is, because it's still in popular use, called HDFS, the Hadoop Distributed File System. It basically created a single namespace that spanned all of the underlying compute nodes. The compute layer on top of that was called MapReduce. And the basic idea was that for a given piece of work, you would kind of the map component would spread that work across the different nodes, and the reduce component would kind of pull it back up and aggregate it. And your programs would basically use this MapReduce idea to do distributed computing. More recently, MapReduce has fallen out of favor because really that MapReduce paradigm is kind of limiting in a lot of ways, and is only applicable to certain types of workloads, and a lot of work had to go into, if you've got a problem, kind of decomposing it into a series of maps and reduces. And so Spark kind of came in the wake of all that to kind of sit in that same Hadoop ecosystem. So it has close ties to HDFS, but it used a different paradigm that was more based around kind of pipelines and graphs and doing things in memory. The basic, oh, my picture's still out there. The basic idea is that Spark kind of, you have a Spark cluster. There are, you can create those clusters in different ways. There's kind of a standalone Spark is kind of, you can run Spark on an individual machine in kind of a standalone fashion, or you can use a cluster orchestrator like Yarn, or Yarn is a kind of the cluster manager that Hadoop uses, or Kubernetes more recently would be used as a cluster manager, or there's another cluster tool called Mesos that is still in use for folks that are doing, massive scale, like thousands, tens of thousands of nodes. But it's kind of going out of favor relative to Kubernetes, which is more recent. But in any case, the idea is that, tools like, Mesos or Kubernetes are used to kind of manage manage the core processes of Spark over lots of different nodes. And those core processes are kind of a driver program, which parcels work out to worker nodes or executors. And so the idea is that, if you've got a program that has some parallelizable component, and that parallelizable component could be, as simple as you've got a large data set and you need to do some operation on it that is, each of it can be done on kind of individual rows in your data set, or, batches of rows of your data set. You can, split your data set up, kind of send work out to a bunch of different workers or executors, and then, that'll be kind of collected. That's kind of a style very much like the MapReduce style. Spark has also seen a lot of popularity in more of a streaming use case, where you've got a lot of, you've got streams of data coming in, like these avail streams, and for each stream that comes in, maybe it needs to be transformed and some analysis that needs to be done on it that is independent of all of the other streams. You can just have all of those, all of that streaming data come in and get parceled out to worker nodes, which will, do their transformations and then land that data wherever it needs to end up. So that is the general idea of Spark. Kind of a core concept in Spark is this idea of an RDD, a resilient distributed data set. Basically, the idea of the RDD is similar to HDFS in that this you load this data set with something like a data frame similar to Pandas, and that data is distributed out over your Spark cluster through the RDDs. And then, so in working with Spark, the idea is that you create an environment. You basically you connect to your Spark cluster from Python. You load your RDDs. You carry out or run some set of transformations, and then you execute actions to get whatever your result is loaded back in Python. And this idea of transformation and action are kind of the two core concepts in Spark from a compute perspective. Any questions before I pull up some examples or the kind of the case study to walk through?
You'll probably answer my questions by doing that, but one of the things that was fuzzy when I went through this was, they talked about lazy evaluation, and I wasn't sure if that was lazy at step 3 or step 4, because I couldn't really distinguish between what does it mean to carry out a transformation and then execute an action. You seem to be like, well, aren't those kind of the same thing? So that line was not very clear to me, and probably your examples will make it clear.
Yeah, I don't know that we'll see that in the examples, but I think the wording in step 3 should be more like specify your transformations, and then when you execute them, it's your graph. So the idea of lazy evaluation is implemented via what's called a DAG, a directed acyclic graph. So basically, you specify the transformations that are going to happen on some data in the form of a graph, or at least under the covers, Spark kind of converts these transformations into a computational graph, and then when you execute that graph, only then are the actions actually happening and the transformation actually happening.
Well, that was my first reading of it, but when they kept saying carry out, that's just a completely different concept than specifying transformations. I'm with you. I wish they had said specify the transformations.
Yeah, let's take a look and see if that if we can suss that out in the example. So before we do that, I'm going to pull up. So I am. So for both the Kubernetes, for both the Spark and the Docker and Flask stuff, I am using Kubernetes here. So Kubernetes is a cluster manager. I basically have it set up just running on the desktop. So this will make more sense when we talk about Docker. But the idea here is the main point to show is that I've got a couple of kind of virtual nodes. This My Notebook Deployment virtual node is the what we call in the picture the driver. It is living on here as well as the kind of the Jupyter Notebook instance. And then the this executor node is automatically spawned when I run my notebook, and I'll show you where that happens. So this is the kind of the cluster environment. It's all running kind of virtually on my machine here. And so you'll see in this is basically the Spark intro that they have you download and run. You're basically, this is kind of the standard setup that we have seen a lot, kind of do a bunch of imports and set up your plot. And then there's some discussion here. All of this discussion is in the reading, so I'm not going to focus on it too much. It's kind of background information. What is important is that the way you set up the driver is you basically create a, you configure Spark, and then you create a session, and within that session there's a context, and then you do everything, all of your operations with Spark happen within that context. And so this is going to be different than what you saw kind of in the standard notebook. And I think I closed that, but basically all of the configuration stuff is telling your, telling PySpark, which you're kind of using in the notebook or Python environment, how to connect to your Spark cluster. And in my case, this is the stuff that I needed to do it in Kubernetes. I'm basically saying, hey, the Spark cluster is in Kubernetes. This is the Docker container for it. These are the number of instances and cores and kind of the memory that I want to use. And then, this part here is here's how to connect to the data once you spin up the executor. And so you run this, and basically you'll get something that is very similar to this. It basically prints out your Spark version, and then it prints out all of your configuration parameters that you just told it. And when I started this from scratch and ran this, that is when this this executor node will be spawned off, and it is sitting there kind of waiting for things to do. And then, so the kind of first step here is, we're starting with this workflow, and basically what we're doing here is we're in the Spark context, we're calling this text file that is going to find this Sherlock Holmes.txt. Is basically a corpus of Sherlock Holmes books. And then we're doing this MapReduce thing that we talked about. So basically the idea is that you've got this document that is full of lines of Sherlock Holmes, and we want to essentially do like a term frequency calculation. And so as opposed to doing all of that on one node, in the Spark world, we can basically split that document line by line, and we can so what the map is doing, it's basically for each of those lines sending a word and the number 1 out to a mapper that is sitting on each of the nodes, and then the reducer is taking the word and the count, and it's kind of aggregating all of those together. And then when you do that across all of the lines, they will be sent out to kind of distributed across all of your executors, and the counts.collect is basically this is where you execute it. So I think, Tracy, this is kind of our specification here, and it's not happening until you do this counts.collect. I need to research that to make sure that that is the case, but
I'm pretty sure, because I do remember reading something else like the caution statement there. The reason they put caution there was because they were saying, look, this is when it's actually going to all go down, so you better be ready for this statement to be the killer statement.
Yeah, I think the other part of that caution is that here you're loading all the results into memory, into the Python environment. Before here, it's all happening kind of distributed in your cluster. And sometimes, you might not want to, or have the, if you're working with a big enough data set, you might not want to pull all of that stuff locally down into your machine.
So that raises the question that when you execute the counts equals text file ... and if you were to just stop there, or if you were to just execute that part separately and then watch your processes, would the workers all be cranking away at that point, or do the workers crank away at the counts.collect point?
Mm-hmm. Yeah, I think so down here we talk about I think it's addressing that here. RDD is a fault-tolerant collection of arguments that can be operated in parallel. API uses two types of operations: transformations and actions. And there's the data frame ML API. On top, the text file is an RDD that, once subjected to a chain of transformations, is used to create counts, another RDD. So this counts is an RDD. The action that we use is collect, which brings the data back to Python, is something you should. So keep in mind, transformations are the way we express the business logic. Spark doesn't apply to transformations. It builds the DAG. Transformations chain together. RDD is immutable distributed collection of transformations on your data, partitioned across nodes in your cluster that can be operated on in parallel. I don't know that that answers our question. I think I also don't know if we tried to look at the kind of CPU, like, there may be caching and other things that that keep us from being able to see this actually happening, but we can certainly try it. Let's see. Why isn't activity monitor showing anything? Of course, Zoom is using up most of my CPU. That was pretty quick. And so it's just returning this class, which is RDD. But if we do the results, that's taking quite a bit longer. Did you see that?
So this would be a classic example of splitting the cells and adding the % time thing and track, measuring both of the execution times, I think.
Yeah, I was thinking that, and I could Google. I always have to Google what that.
I know.
I
Well,
can
that you should say left as an exercise to the student.
Yeah, exactly. But I think even just kind of observationally, like that's very quick, and this is taking a lot more time. And so what it's basically doing, again, it's kind of, it's the results here are the first 7 returns or results from this collect, which are just kind of words in the corpus and their counts. And so the next one, we are creating a bunch of random numbers, 500,000 of them. We are creating a RDD that parallelizes them. And then we are, let's see, divide by 3. So we're, the transformation that we're applying is this, filter that applies a function to, is it divisible by 3? And then we'll return a 1 if it is, and then we're doing a count. So RDD count, this is total 1 is our, just the total number of items in our RDD, and then total 2 is the number, it's aggregating the number that are divisible by 3. And again, I think we can probably do, if we do this, well, parallelize might be, yeah, see where there's the kind of state issues with notebooks, so that those were already defined. But I think the parallelize might be taking up some of the time there. But they talk about this again here. So lazy evaluation, count or collect is sent for execution. That's when we're executing the transformations. This time we'll use it with a NumPy array with a parallelized function. The transformation is a simple filtering the actions or to obtain counts. I don't know if this is going to help us, but I'm curious in what way it's parallelizing and what the, we need some documentation, like how many, there we go. Partition across the nodes of the cluster that can be operated on in parallel. All right, so where's my notebook? I think what's happening here, we're creating this, we're creating these numbers as basically a NumPy array, but they don't, they're not in Spark. So here what we're doing is where the parallelizes, if we had, right, in this case, we've only got 1 executor, but if we had, 5 executors, these random numbers would be distributed across the 5 executors, and our RGD would basically be a kind of an abstraction or a pointer to all of those. And then this next one is, what they're trying to show you with this next one is there's a Spark submit command, and basically using Spark submit, you can set up your Spark context in a Python file, create a function, and you can write this out as a Python program, and Spark submit will execute your Python function kind of with Spark. The idea is like we've talked about earlier in the course, as opposed to kind of doing everything in notebooks, ultimately you want to create a runnable, repeatable artifact. And in the general case, that would be Spark submit. Here, because I'm using Kubernetes, I would have to do things differently and kind of build up this Spark context, and I did not do that. So I just kind of commented it out so that we can see, what this is doing in Spark, but we're not using that Spark submit function or executable. But basically, this is trying to estimate pi. So we're creating a bunch of random numbers, or the function is creating a random number and returning 1 if that random number is kind of within a circle, basically. And so here again, we're kind of parallelizing a bunch of I'm not sure what this.
Isn't this drop a pin on parallel lines, and if it crosses, count the number of times it crosses the line, and that's the pi estimator or something?
Yeah, although I'm not sure why. Like we're passing it p, but p isn't.
Oh.
Here.
That's funny.
Interesting. I wonder if map sample. Yeah, the Spark Pi is like it's kind of the standard. It's one of the examples that comes with Apache Spark. It's kind of a standard example. And it does the same thing here. Parallelize, frame the filter. All right, this is what I'm going to have to track down, but I'm assuming that that's just not used. And basically, we are, okay, so here we're coming up with a bunch of 10 million numbers and kind of sending them around, and then we're mapping those to sample. Yeah, okay, so I think what we're doing here, okay, this makes sense. I think we're this parameter p is really only because we need to, the map is going to pass it something, and so it needs that parameter, but we don't really care. We're just taking random numbers, and we're again, seeing if the kind of random numbers are within this, circle of radius 1. And then we're counting the number of these random numbers in our 10 million runs are within the circle of radius 1, and that's how we're estimating pi. Okay, that makes more sense. And so can execute that. This would be the one where we should do our separate our parallelize and our count, and see where the time takes, since we're doing so many of these. But in any case, it ultimately writes this out to a file, and if we just get that value, it does a pretty good job. We can try this RDD equals and see if I'm getting this. All right, so oh. Oh.
Didn't you say that cell is not going to work? I mean, all you're doing really is writing the file. No, you're not doing it because you haven't commented that out. But you don't have Kubernetes set up for this, so that's not going to work for you, is it? Or is it leveraging your previous Kubernetes setup?
It is, yes. So because I commented this out, I'm still using the Spark context that is in my Kubernetes environment. So this is, I guess, this took a while also because the parallelize thing. This is another example where I think we'd want to do the time thing that you mentioned. And yeah, we'll leave it as an exercise. But if we do this count RDD, I guess we can comment that out. Rawr. All right, in any case, that's our pi estimate. And so that is Spark in a nutshell. This is taking a little, seems like a little longer than that, but yeah, we'll kind of leave that as an exercise. But before we go on to Docker, any questions about any of this stuff, Spark or the intro exercise?
I just found that their examples, I'm kind of not remembering in detail at the moment, but the setup stuff seemed to be old. Like I remember going out to the IBM, to the Watson stuff, and they said, "Oh yeah, we don't actually support this. I mean, we kind of have the back rep support, but we've stopped supporting it." And then when I looked at one of the Spark installs for Docker, it was like 4 years old and using old script. So I think it sounds like following your Kubernetes path is probably the best way forward.
Yeah, I don't know that I recommend it. You know, I have on my list to kind of write it up, but I spent many hours in trial and error trying to get it working. but I think doing it in Docker, so Kubernetes is just another layer of complexity on top of Docker, but I think there was a example of in the course material of setting up Spark on Docker. And if not, I think that's probably where I would start. Just find
Yeah, that's the one that's like 4 years out of date, I think.
I would think it wouldn't be too hard to find a current Spark Docker image. We don't want that. We don't want that. Well, let's see if they. This is. Oh, that's right. That's right. So, if you go to the Spark downloads and you download Spark 245 with the pre-built Apache Hadoop and download that, then you will you get your zip file, you unzip it, and then there is you run this this command that's in the download that is docker image tool.sh, and you write /bin docker image tool.sh build, and it will build the Docker images for you. And so, well, I guess these are my images here. It'll create a Spark R, a Spark Pi, and a Spark, I believe. And this Spark Pi image, you then Docker run that, and that's a current image of Spark 245.
Great, that's really helpful. Appreciate that.
Now, I haven't done that method. You'll still have to the next step will be to figure out, basically what your connection string is, what this needs to be. But it's probably going to be a lot closer to what they had originally than, what I've got here. And if you run into problems with that, let me know and I'll try to figure it out. So, Jose or Jess, any questions on Spark?
No.
All right, cool. So the next topic that we're talking about here is Docker. Basically, the idea with Docker is that probably best thought of in kind of a progression from you've got a computer, hardware running an operating system, and in that world you install software on your operating system and you run it, and if you're kind of working by yourself and you're only running one thing, that generally works fine. But then once you start kind of iterating in different versions of your software and all of its dependencies, you run into problems. So for example, if you want to say you're working on an app that has two versions of one that's using Python 2.7 and the others are using Python or Python 2 and the others are using Python 3, that can be difficult to deal with. And so kind of the next step in the progression is virtualization. And so you can create virtual machines, and each of those virtual machines is running in your host operating system. And the virtual machine basically has a guest operating system that runs in the host operating system. And it's kind of a self-contained, self-contained virtual computer. It's got your VM typically, has a disk image that is, it can be, quite large as the entire span of the disk that you want this virtual computer to have. Again, it's running a guest operating system. And I think those are kind of a couple of the drawbacks of virtual machines, is that there's a fair amount of overhead associated with running the guest operating system, and you're also dedicating the disk that your virtual machine has to the VM. And so as a result of that, on this computer here, which is a fairly old iMac, generally I can get away with running a VM or maybe a couple, but then it starts to get pretty dicey performance-wise because of all of that overhead. And so more recently, the industry has started to look towards Docker, which offers similar ways, a similar ability to isolate different environments, but it does it within the domain of the host operating system, as opposed to requiring all these guest operating systems. And so the basic idea is you can build these what are called Docker containers that constitute an image or a containerization of some software payload, and deploy those out to any machine that is running Docker. And as long as the machine is running Docker, it will create it will kind of pull down all of the dependencies that you need when it's deploying this image. And so it kind of enables this idea of like write once, run anywhere. And Docker has kind of spawned a pretty dramatic revolution or transformation in the way folks are building software, both traditional software and in the case of ML and AI, and helping organizations overcome challenges associated with, people talk about kind of this canonical problem of runs on my machine, where in the old world, a software developer would be working on their laptop, or a data scientist would be working on their laptop and get something working, whether it's an app or a model, and then hand it over to a operations person or a ML engineer and say, okay, get this, put this into production. And that person tries to run it, and it just blows up. It doesn't work for them because of some set of dependencies or interdependencies that aren't working. And that has historically been a pretty big problem. What Docker does is it kind of the Docker file specifies all of those dependencies, and when you deploy when you build an image, it kind of builds it from those dependencies. And so in theory, that image that you create can be run anywhere without without worrying about this kind of runs on my machine but doesn't run someplace else. And so I think the materials refer to tutorials or a Docker, what is it, this, what's the starting point here? Refers to this tutorial that I think will have you first set up Docker and then build and run your first container and kind of walk through that process. I'm not going to go through this in a lot of detail, but I'll talk through kind of the major steps. So this is an example of a Docker file. This is the Docker file that I'm using for the my kind of notebook node. It's basically, you can set a base image, which in this case is an operating system, Ubuntu. And it is basically pulling down that Ubuntu image and installing a bunch of dependencies. And then at the very end here, setting a bunch of environment variables. And so you would, once you have that Docker file, you would all the way up here, say, I think it may be another window, but basically Docker build. And Docker build basically looks at the Docker file and runs it and creates an image. And then if you look at Docker images, it will show you a list of all the images you have in your kind of local Docker repository. And then you can, there are commands like Docker run, which will run an image. And well, there was a Docker, it's not ls, it's Docker ps, which will show you your running images. Basically, you when you're using Docker, you're kind of, again, building these images and then running these images, and then you can like connect into a shell into these images, into the running image, and operate in the environment of the running image, or you can do things like set up proxies where you're accessing from outside of the image processes that are running inside of the image. And we will see a little bit of that, I think, in the next exercise, which is looking at deploying a model out via Docker and Flask. I don't think I have any particular notes on Flask, but I can talk through it when we get here. So the next tutorial in this unit is a Docker tutorial. Basically, we're starting by doing some imports. We are setting up a processing pipeline. This is analogous to what we've done several times in the past when working with this Avail data set. We're specifying a set of our numeric and categoric features, and then we are creating transformation steps using the sklearn pipeline, where we're, in the case of the numeric features, we're imputing missing values and applying a scalar. And in the case of the categorical features, also imputing, missing values and doing one-hot encoding on our categorical features. And then defining a preprocessor that basically applies these transformations to the appropriate columns. And then here, this is a function that is loading our Avail data set. And this is already run here. These are some examples of a quick reference of Docker commands. I mentioned a few of these. Your Docker PS, Docker container ls is the list your running containers, or another way of listing your running containers. Docker images will list your images. This is just creating a data directory that we're going to work out of for this example. And then here we are building a random forest classifier. So we're loading the tests and or our data set and our labels using that load avail data function. Then we're doing our test train split. As we've done a few times before, we're setting some parameters here and specifying our classifier as a random forest classifier with 100 estimators and a max depth of 2. And then we've got our pipeline set up to be the preprocessor that we talked about, followed by the classifier. We're fitting the pipeline with our training data, and then we are doing a predict step on our test data, and then printing out our classification report, and that's here. And then we are basically dumping the model using the this joblib function. So joblib.dump will save the model to a joblib file. So this is all stuff that we've seen before. The next step is to create a Flask application. So the basic idea with Flask is that it is a web application framework for Python, and it's very simple. You basically import Flask, and this is establishing your Flask context. So you make this call, and then what Flask allows you to do is to decorate functions with routes. So the idea is that when you spin up we'll take this file, which is our app.py, a Python file for our Flask app, and we'll call either Flask run in the directory or Python app.py. And what Flask does when it starts up is it spins up a web server, which is basically a process that's listening on a port for HTTP commands. And when it gets what Flask does in its essence is allows us to map functions to routes. So here, when we run this app, it's going to start listening on all the IP addresses on the machine on port 8080, and it is going to, and once it does that, if we hit, actually we can do this because I think I still have it running here, but on port 4000, this is basically our root. So we did a call to this localhost 8080, or 4000 as the case may be, /, and it is returning to the browser the HTML that we're basically telling it what to return in the browser. In this case, we're building up hello name, and we're returning hello name and the host name, and name comes from our, either our environment or the default is world, and host name comes from, asking the operating system what the host name is. And in this case, this is, I think, the idea of the running Docker container that this is in. And we could also hit the predict endpoint here. It's returning an empty list because we didn't give it any input data. But if we did give it input data, it would take our input data, create a pandas data frame out of it, put it in the right format, run an inference on it by calling model.predict. In our main, we loaded our model here. So model.predict will do the inference, and then it'll return a JSON representation of our results. So this is kind of Flask in a nutshell. Any questions on Flask? So to what degree are you familiar with Flask as a tool, or the concepts that I'm talking about here? Is this familiar to all or any of you?
I've done the equivalent of hello world in Flask.
Yeah, pretty much the same.
Yep, similar.
Okay. So this is basically hello world for ML models in Flask. And so hopefully that if you weren't very familiar with Flask, that explanation of what it's trying to do makes sense. What we're doing in this exercise is we are writing out our Flask application here, and then and here you can do, because we're in a notebook environment, we could do things like test our predict function independent of the Flask machinery, and then when we're done, use this write file magic to write out the app.py function. And then you can run the app.py function and pull it up on a browser, which we did. And then we're so we've got this kind of working Python web app using Flask that exposes our model, and now we want to containerize it. We want to create a Docker container. So there are a couple of things that we need to do in order to do that. The first thing is, or the main thing is, really to create our Docker file. This is analogous to the one that I showed previously. What it is doing is starting from an official Python 3.7.5 image. So this has probably a very minimalistic Linux kind of operating system core. We are updating it and installing the Python 3 dev tools and essential tools that we'll need. Putting our files into a /app directory, and then we're installing our Python requirements, and we've created those here just by writing out to a text file. But to run this Flask app, we need NumPy, Flask, Pandas, scikit-learn, and we're also using the Python here. And then we are kind of exposing actually this was, I think this was a mistake here. I think you need to make this 8080 in order for it to work, because that's the default Flask, the default port that Flask rather is going to spin up on, unless you explicitly tell it to start someplace else. But you basically write all of this stuff into a Docker file, and you go through the steps that I mentioned earlier. You go to the directory where you have all this stuff. You say Docker build, and Docker build dot basically is Docker telling Docker to build a image using the Docker file that it finds in the current directory. The -t is allowing you to name or tag your image, and then you can see it in your list of images. And then you run it by saying Docker run, and then the name of your image, which you gave it here. And what you're doing here is this -p is telling Docker to map the port that is running inside of your container as 8080 to 4000 running outside of your container. You might want to do that because 8080 is a kind of popular port. Maybe you're experimenting, you're running Flask outside of the container, and it's going to be on 8080. And so if you don't map your port, or you map it to 8080, you're going to have conflicts. So here you're just kind of mapping it to a different port. And that's what I did previously that allows me to run, to hit this web Flask app on port 4000. So now we've got a Docker container that's running our Flask app. And so we go and make sure that it's running, and then we are going to create some input data to do an inference here. And so what we're doing is we're creating a new dictionary. We are adding we're basically kind of populating a list of 5 rows with the fields, country, age, subscriber type, and num streams. We're turning that into a pandas data frame, and we're just kind of here just displaying it. And then this next step is we are importing requests. Requests is basically is the library that you use to issue HTTP requests. It's kind of like doing within Python a curl or wget, if you're familiar with those. And so we're creating in order to do that, we want to send our query. So we are this xnew that we created above, we're turning that into a dictionary and setting that to query here. And then we want to hit our Docker API with this request. And let me see if this was still not working. So the problem that I am having is that this notebook for me is running inside of Kubernetes, and the Docker that the Flask app that I created, don't remember which of these tabs it's actually running in, but it is running outside of Kubernetes, and because of that, the two, okay, here it is, the two can't talk to each other. And so this isn't going to work for me, but what I can do is, let's see. I could, I could say query, for example, and this is basically a JSON document. And I can go to this dev, where is this? Is that in here? No, it's in dev, Kubernetes volume, Docker tutorial. And I can cat out to query.json. And I can let's see, how would I do this? All right, let's see if this, something like this will work. So I want to be here. So I'm going to want to call my local web server 127.0.0.1:4000/predict. And I want to send this format actually works, query.json. I can just put this all on my mind. All right, so let's see if this works. Expecting property name enclosed in double quotes. So it didn't like my query. So let's see if this quick trick will work. I think it will like that more. So let's try this again. That did not work. Expecting property. Mine one near column 20. Is that my? All right, so let's. You want to be. Let's see. So that error is waiting property line 1, column 20. Oh, so that's going to be our input. I'm not sure what is not liking about that. All right. Oh, let's see. What else could I do here to try to do this? Have any of you ever used a tool like Postman? It's like a IDE or like a testing tool for APIs.
Yeah, I've used Postman a bunch. It's been a few years, but I built a mobile app like 4 or 5 years ago, and I used it all the time to test my REST API. But it's been a while.
Let's see.
It was really useful, right? Because you could always see your response and ping it over and over.
Yeah. Yeah, I'm hoping this will.
Missing his ear.
Good. Yeah, and I think I can. Yeah, so post and let me look in my app again. So query equals person. It's just looking. May need to send it as a.
This is my, I mean, I should know this. This is embarrassing to even ask this question, but your keys are just numbers in your JSON.
Key.
Did those have to be quoted like 0, 1, 2, 3, 4?
Country. That actually looks kind of weird. I think that might be. I think maybe the problem is related to that. Let's see. Because these are this is a list, but a list in JSON would be a bracket, and it wouldn't have let's see, format port JSON equals query. Yeah, I wonder if it was. I don't think you want it to be those to be quoted because then it's creating a dictionary with those as keys as opposed to something that's more like a list. But usually you would see a list like with the brackets and without the numbers. So let me just see if I can refresh myself on send JSON Postman. All right, close raw. Let's try that. So let's get rid of the. Let's see if this does anything. Urgh. Well, so right now what's happening is not that it is, right now the issue is that it's just not seeing it. And so we're, let's see. That's our response. Try this. That might have made it blow up. So we're posting. So we should be looking at this.
Can you just, just a quick test, do a version of your query that just has one line in each of the categories, and then just for fun, put quotes around the numbers for the keys?
All right, so let's look at, let me just make sure that it's seeing something. So it's seeing that. So you want a query that looks like, that has quotes around these?
Yeah, just like do one each. So one country, one age, once, just to see if it's. And get rid of the commas.
Guys, I'm sorry to do this, but I'm not at home and my laptop's about to die. So, because we're traveling around dropping off these masks, so I'll catch up with the video and the rest. But thanks for today's session and great to talk to all of you. And Jess, I hope you feel better too.
All right, Jose.
Stay well, Jose.
Take care.
All right, thanks, guys. Talk to you later.
All righty. So we want to do this, and let's get our so yeah, it's not liking that either. So it's posting, it's getting it, so it's just not returning anything interesting. So we can go to our app here, and I guess we can't change it because we need to rebuild our Docker image.
Sounds like another left as an exercise to the student.
Yeah.
So did I understand you right that if we solve these things, we get a discount on some of your T-shirts or something?
Exactly. Well, I think you, Jess, and Jose will definitely get T-shirts, no question. Solving this or not, but
Woohoo.
Good times.
Absolutely.
I'll wear it with pride.
Nice. So I will figure out what the heck is going on here and report back to you. we will discontinue the live coding session for now. But basically, the idea is that, you know, outside of these kind of infrastructure and formatting issues, and I'm fairly sure that that one is pretty silly and would be pretty easy to figure out once I'm not under the pressure of the camera. I will, you know, basically we're going to call this predict. It's going to pass that JSON query that we were mucking around with to the model. The model is going to, you know, it's going to pass that to the predict function. The function is going to run the inference. It's going to return the data. Flask is going to return that to the browser, and we should get a JSON blob showing up on the screen. And so that the idea is that now we've got this containerized model, and I think we're not talking about it in the course this time, but you know, with that Dockerized containerized model, we could then deploy that onto a Kubernetes cluster. And if this Kubernetes cluster, you know, say it had, you know, hundreds of machines, we could specify a replication set that said that we want, you know, hundreds of these Flask. This is our Spark. We want hundreds of these Flask instances, containers running across our cluster. And then Kubernetes, you know, has these load balancing and ingress features where we could have a single. I think what's happened here is that my token is timed out, so we're not going to worry about this. But Kubernetes has, you know, one of the things that it does is load balancing. So our cluster and that namespace, the Flask, kind of this Flask deployment, will have a single IP address and port, and we can hit you know, Kubernetes cluster :4000, and that request will get distributed across, you know, one of the hundreds of running containers running our inference app, and it'll do just what we're trying to do here and return the value. And so now we've, you know, scaled up our capacity to do this inference by, you know, 100-fold. And that is the advantage or the benefit of, you know, what we were doing in this example here in containerizing this model. So that is, that's what I've got for you today. I will try to clean up what I've done and put some, you know, figure out these last couple of issues we saw and share, you know, what the issue was via the Slack. But beyond that, happy to take any questions that you have.
So you're also going to maybe write up just if it's easy to do, the problems you ran into with Kubernetes, or at a minimum, sort of what you found that worked, maybe not necessarily being explicit about your rabbit trails, but in case we want to, you know, throw a couple of hours of our life away trying to do that.
Yeah, if you're interested in playing around with the Kubernetes solution, I can write up my, you know, I'll basically kind of blow it all away with kind of lesson, you know, with what I, you know, retaining what I've learned and try to recreate it and document that, and can share that, you know, in a GitHub repo or something. Would that be useful?
Yeah, seems like you're pretty big on it, so seems like that might be a good thing to at least attempt.
Yeah, and it comes up later in the course as well, so maybe it'll be, you know, get us ahead of course 6.
Excellent.
And you're on Windows, Tracy?
I kind of go back and forth between the Mac and a Linux distribution. So I'm on Ubuntu 16.4.
Okay.
Um,
So
I'm-
I'll be doing this. I'll write it up based on using Docker Desktop on Mac, but that part of it is pretty standard. As long as you've got Docker running somewhere, then most of the instructions will be the same.
Yeah, I mean, I guess it makes sense, but often the things I'm the most interested in are the things that I don't know as much about. And this is definitely in that territory. So most of what we were talking about today, I would like to dive a little deeper into. But if I was going to kind of try to target my time to the best learning resources, I would love suggestions for what those would be. Because a lot of times, I feel like resources around these tools are kind of geared to people who almost already know how to use them in a sense. So I'm looking for more basic material to build a foundation and then kind of get into some of the more advanced material. So if you have any ideas or suggestions for that, that would be great.
Yeah, I've got a boatload of tabs open. I can kind of go through and kind of curate what the most interesting ones are. Were there any particular of the tools that we've talked about that are of most interest? Is it the kind of Docker Kubernetes stuff, or the Spark, or Flask, or kind of all of the above?
I guess it's kind of all of the above. If I had to pick between them, I would say probably Docker and Flask are maybe what I'm most likely to use more immediately.
Yeah.
But then I think the others are just kind of more for my own intellectual curiosity. I don't know that I'm working at that scale, but I'd certainly like to know more about it. So that's kind of how I'd prioritize them.
Okay. So then
I'm just dittoing her.
Okay, so then I will I think in my write-up of this, I will on the Docker Kubernetes side kind of go all the way through to the Flask app and point out some resources there to fill any gaps. And then on the I think I'll just point to, well, I have to think about how to structure it. To do, if I do separate things for the Spark and the Flask, you know, maybe it's different parts of the same article or something like that, or series or something like that. But I'll you know, pull together pointers that I found useful. A lot of this stuff, the stuff that I was looking at was very kind of low-level tactical, like how to install and pull stuff together, as opposed to kind of higher level how to use, like how to use Spark is a huge topic and probably the subject of, you know, standalone courses. I'll try to see what I can come up with there, but it may be you know, pointers to documentation as well. But on the Docker and Kubernetes and Flask topic, there are a lot of interesting resources, and some of which, you know, the basics that you need to understand, I can just explain, you know, via Q&A or writing it up. So.
Okay. Yeah, thank you.
Sure. All right, cool. Well, unless you have any more questions, I hope you both enjoy your weekend.
Thanks, Sam.
Yeah, thank you.
Especially thanks for staying up till, like, what did you say, all nighter? You were like till 4 in the morning or something?
Not quite 4. Not quite.
That's good.
2.
2.
But, you know, you know, at least I'll remember how to do this for the next week or two. And then if I have to do it, you know, more than a couple of weeks out, it's another all-nighter probably. But
See, that's
writing it up writing it up. I think is a good way to make sure that the next time I have to do it.
that's really why we've asked for the write up. It's for you, Sam. It's for you.
We're trying to be really helpful by knowing as little as possible.
Help me help you. I forget what movie that's from. Yeah. Cool. Yeah, I'll keep you posted on that. I'm not sure. I will make some progress on this between now and next week. Hopefully, at least get a kind of skeleton pulled together that you can follow along with, but it might not be super prosaic by then. But I'll keep you posted.
All right. See you on Slack.
All righty. Take care.